We'll now start with example 2 to find y of t, and we are given x of t, the input, as well as 0 initial condition again. So this example is still simple, and then let's find. Right, okay, x of t now is no more the single complex exponential. We now make it cosine 1t. So remember, cosine 1t is nothing but sum of two complex exponential. We again use the same h of t, which is e minus 1t, and we are asked to find yt. No, so in time you have to perform this convolution integration, but it's impossible to do because we can't get some numbers out. So what do? Well, we do the next best thing. We want to try to solve the problem using the Laplace domain. So what do? Well, the Laplace transform of e minus t is 1 over s plus 1. So this is by lookup table. The Laplace transform of cosine 1t is s over s squared plus omega naught squared. Omega naught is 1, so it will be s over s squared plus 1 squared. So convolution becomes multiplication, so we have ys equals to these two expressions multiplied together. And since we have initial conditions to be 0, well, let's see what happened later on. Okay, now it's so what do? This is we need to find something like a over s squared plus 1 squared plus b over s plus 1. So this process is called the partial fraction expansion, and I know you have to do it by hand, and of course what I do is I use MATLAB to get my results and check, and you can use your MATLAB results to check. Alright, how to get this answer is we have the numerator, so the numerator is s, and s is order 1, so we represent it by a vector called 1, 0. So this is the numerator of the ys. 1, 0 represent s. So this is saying that I have 1 with a power of, at power 1 the value coefficient is 1, at power 0 the coefficient is 0. Alright, second is s squared plus 1 multiplied by s plus 1. So if you have to do it by hand, you do it this way. You will take the two factors and you open up the bracket so that you can multiply them together, and then you have this expression over here. I'm lazy. I just use the convolution to perform the multiplication of this polynomial, and I first describe what is s squared plus 1. So s squared plus 0s plus 1 to the power s0. So the coefficient is 1, 0, 1. So this is it. What about s plus 1? So s plus 1 is s to the power 1 is 1 coefficient. S to the power of 0 is also 1. So this is 1, 1. Multiplication is convolution of these two vectors, and you will get the same answer. So in one line, I use the MATLAB to extract my partial fraction solution. So this is it. You can go and check. And R is called the residual. This is R0, or I should say R1, because MATLAB likes to do things in index 1, R2, this is R3, this is P1, P2, P3, and then K is 0. So once we have RPK extracted from this residual, what we can then do is to use these coefficients and put it in this form. Now our roots are distinct, our poles are distinct, -1 plus j0 plus j and minus j. So there's no repeated roots. So it's very simple. So first is we take these poles and we put it at the bottom. So this is s minus p1. So what is p1? -1 plus j0. So it's s minus -1. So this becomes s plus 1 later on. Alright, the top guy is r1. If the bottom guy is p1, the top guy is r1. r1 is -0.5. So we now know how to get. This is actually r1 divided by s minus p1. Okay, second guy. This guy is r2 over s minus p2. So let's see the coefficients. This is r2, 1/4 minus 1/4 j. S minus p2 is s minus j. Alright, and this of course is r3, 1/4 plus 1/4 j. This is s minus p3. So this is p3 here. Alright, so we now know how to go from rpk to the partial fraction expansion. Once we have the partial fraction expansion, then what we can do is lookup table. That's it. Although this guy don't have a lookup table, so we have to convert it into something that looks more like this. Now this have a lookup table. Okay, this guy have a lookup table. This guy have a lookup table. Let's go and look up the table. So on the left, it's very easy. This becomes this guy. On the right hand side, it's also quite easy. You realize that if you convert this into this form, this is a cosine 1t, this is a sine 1t. So we have an expression here plus a cosine 1t plus sine 1t. Okay, let's remember what we have just said. Our input is a cosine. Our output is a cosine, a sine, and a what do you call that? An exponential that is decaying. But didn't I just told you that when you send a cosine in, out comes a cosine? Why do you have three things now? Okay, don't panic. Look at this term. When t is equals to 0, this is -half. But when t equals to infinity, what happens? Then this term disappears. So this term is the transient. It only exists for a short time. At time equals to infinity, this term is completely gone, leaving with a cosine and a sine. But didn't I just tell you that if you send a cosine in, out comes a cosine? So what gives? Right. So remember your what do you call that? Your sum of angle rule. You can change this expression into this expression here. It has a magnitude and a phase shift. So this is the magnitude and this is the phase shift, and you see this is your cosine at 1t. So we have sum of cosine and sum of sine with some magnitude will result in still a cosine of 1t, but with a different magnitude and a different phase. Okay, that's the idea. So if you forget this, please go into this math center and type this. So I Googled this for you. There is some very nice tutorial to say that a cos x plus b sin x. So you replace x by 1t. A and b are different coefficients in our example. They are both half. And you realize out pops a magnitude. In here you put r. And out pops a phase minus alpha. Now, if you go to this, you will see that the description of why it happens is here. Okay, so it proves why r cos x minus alpha is equals to the sum of cosines and sines. So this is this you should know in the past, so this I will not repeat. Now, I did it by hand. Of course, I can do it by MATLAB or Python, whichever you prefer. And so now I will show you the graphs that I can produce, and I tell you what it means. The blue line that you see here, this blue line is the input. It has amplitude 1 and it is a cosine because it peaks at when time equals to 0. When time equals to 0 is amplitude 1. Okay. Now, what about the complete response, which is, let's see, this transient which is this transient, yeah, minus half e minus t. Where is it? This green line over here is minus half. It starts from minus half at time 0 and it decays. So this line is minus half e minus 1t. Alright, what about this guy? 0.7071 cosine t minus a phase shift. So it's a cosine of amplitude 0.7071. Okay, where is it? It's this guy. Is the green bubble guy. This green bubble guy is the cosine. Notice that it has phase shift because the peak is here. So it's delayed by this angle. In fact, if you calculate the angle, which is minus 0.7854, 0.7854 is minus 45 degrees. So you can see it here. The peak is at how many? 0.7071. Right. So that green circle guy looks like a cosine wave swinging up and down. Doesn't change. It's called steady state response. So you realize that the complete response has a transient and a steady state. So this guy is a transient, this guy is a steady state. Let's add them up. When we add these two guys up, you will get the red line. So the red line is the complete response of the cosine when the cosine starts at time 0. So what happened is that the output doesn't become the steady state. The output is due to that circle and that straight line. It will start from time 0 and it will swing up, it will grow, and after a while it will follow the green line to become the steady state after the transient dies. So the transient dies about maybe 5 seconds. Alright, so now you appreciate that we have a transient as we are sending a cosine into a system. Why a transient occurs? Like the inertia of the system. It takes some time to warm it up and to become steady state. Okay, now the whole exercise is done within actually these 5 lines of code or 6 lines of code. Okay, we will initialize omega equals to 1, the phase is 0, and then n times 20, and we'll P1 is exponential minus 1t. So the impulse response is exponential minus 1t. Hs is nothing but Laplace transform of the impulse response. X of t is cosine 1t plus 0. X of s is nothing but Laplace transform of x of t. Ys equals to h of s multiplied by x of s. Y of t is inverse Laplace transform. And that's it. Within these 6 lines, we have finished the whole thing. Of course, now we can plot. So the plotting is trivial. So just see how we plot. And we get the answer. Okay, go ahead and try. And you will see you'll get the answer on the right hand side. Now, let me highlight something to you. The frequency response. Frequency response. Remember what is frequency response? We take h of s and we substitute omega. So what are we interested in? S equals to J1, because J1 omega is 1. Is the input we're interested in. Cosine 1t. So we substitute this into here by J1, and then we get this. This is a complex number. We convert it into the polar notation, and we get 0.7071, which is 1 over square root of root 2, e minus j 0.7854. So we have a magnitude and a phase. And what does magnitude and phase do? This magnitude and phase says my original cosine, which is amplitude 1, will now change its amplitude to become 0.7071. Originally, my cosine has a phase shift of 0, which is here. So the peak is there, but now the peak is here. It's shifted by 45 degrees, delayed by 45 degrees, or delayed by minus 0.7854 radian. We prefer to do everything in radian, really. Okay, that's it. And we are done with the Hs and Hj omega in this section. Thank you.